So I think we are ready to go. Good morning and thank you all for coming to the talk. And sorry about that broadcast message. And those of you who tried to get into the share this morning probably couldn't. Anyway, so Matt saved the day by turning off permissions to everyone except the group members. Okay, so our group is focused on what we call interactive visual media. And sort of before explaining what we mean by that, I want to start with a little bit of a prelude. One thing I think that's sort of a premise that everybody seems to agree these days is the future of the PC implies rich media experiences. And basically there are three factors that are determining this, right? The imaging and graphics capabilities of the PC are rapidly growing, and they're going faster than...
Get in front of the mic.
Okay.
No, you're fine.
Okay, sorry. Okay, yeah, the imaging and graphics capabilities of the PC are growing faster than Moore's law, and we are really not fully utilizing that vast power, except in cases like games, which is of course something that my kids do in the evening, but during the daytime, when I'm working, I'm not really exploiting that power. It's almost like I have two different computers in my computer. Of course, everybody has a digital camera, at least in the Western world and Japan. And video acquisition is also very popular. But while we are collecting this amount of data, they're just piling up in digital shoeboxes. We don't have very good facilities to do what we want to do with them. These being rich memories of our experiences, we want to share with people, storytell, and things of that sort. And lastly, of course, the much promised increase in connectivity means that media is going to be delivered to every computer in every home one of these days when broadband really happens. Right? But we'll sort of believe that for this moment. Now, basically, if you look at the PC visual media experience today, the viewing of video and imagery is largely passive. Okay, images you could maybe a little bit rotate, and if you're lucky, do some red eye correction or something like that. Any kind of editing and browsing of timed media is very much based on a timeline concept, which works well for people who are producing movies and high-end editors, and where they want precise control over things, and they're used to putting in this effort and actually get paid for it. But it's not something that translates well into any other space. Even the enterprise worker, leave alone the home consumer, is not going to be happy with this kind of UI. Searching in content is really not sensitive to the content itself. I mean, especially in visual media, we have a long way to go there. And we can do some annotation and storytelling, but even annotating a document, leave alone media like pictures and so on, is somewhat tedious, and the annotations aren't handled properly. They aren't always kept and shared, and they are by and large somewhat secondary citizens. But largely, in any kind of an inter-exchange setting where people are sharing documents and so on, annotations sometimes are as important as the content of the document itself. Whereas our support for that is not really all that great. And of course, in terms of playing, each media basically lives in its own box. Pictures have these rectangular picture boxes. Videos play on a player window, and you can't really merge seamlessly those kind of media, say for example with some graphics or animation that you might want to put in. And it takes an enormous amount of, again, developer effort if you want to build a web page that these kind of things can coexist and play seamlessly. So sort of the goal of our group is simply to look at different ways of making this possible, different ways of making the PC media experience much richer. And sort of the two basic, overall premises, what we are targeting is we want to make the content interactive. That means we can actually, rather than touching just the buttons on the player, we may want to be able to actually touch the contents and something happens when that's done. And this could be, documents, presentations, pictures, video. It really shouldn't matter which kind of content it is. And secondly, of course, ultimately, in one important space is social interaction. And what can we do in order to annotate the content, augment the content, providing capabilities of browsing and searching, storytelling, making new kinds of presentations that will simply allow us to make, have much richer ways of interacting with other people through the media, because that's the primary purpose of collecting a lot of the media. And if I try to divide our group's agenda in some way, I just decided it has to be 3 parts, because the number 3, as we all know, is important. So these are the 3 that we could come up with. You could come up with many other divisions. One aspect of our work is doing what we call media content analysis, looking at new representations of the media itself, but going beyond that, perhaps doing some intelligent processing and modifying the content, but maybe even going to the point doing some kind of perhaps recognition, indexing, and things like that sort. Right? And the second part is, okay, we want to enhance people's experience with media, so we start with today's media, just flat documents with annotations, presentations, video, pictures. How can we make the experience and interacting and using those kind of media much richer than today? But then we don't want to stop there, and third part of our agenda is actually going beyond that to create what we call new types of media experiences, which are just not really part of any single media type as it exists today. So the different things that you would hear about today in the talks that we give would actually cover different aspects of these things. Now, the kind of impact that we're having on Microsoft products, I tried to summarize it very quickly in one slide. I'm not sure I've covered everything. There's a bunch of work that's going on in the area of improving the layout and reading experiences. For instance, adapting the layout to the size of the window so that the content looks richer. You'll actually see a demo of that, so I won't say more about that. We are working with the eDocs group and the tablet PC groups to make this happen in real. And we're doing a lot of work on annotations. There's the common annotation framework, which started previously about a year or two ago in Anoop's group and has now migrated over to our group. And we'll tell you about where that's going, and that's going to be part of the next version of Office and so on. And again, the same framework is going into Avalon or eDocs and in tablet PC. And a related thing is dealing with inked annotations and how the experience with that kind of medium can be enhanced. That's something we are working with the tablet PC group as well. In the area of video, we are working with the Windows Media tools, namely Movie Maker and Producer groups, to look at new metaphors, new approaches for thinking about consumer video and how consumers may want to share it and experience it. And some of those ideas, jointly working with them, are going to migrate into the shell itself. And we are working with the shell MSX. I think MSX stands for Microsoft Experience, and which is they're prototyping a bunch of what kind of a future user experiences the shell would be. And we are working a bunch of stuff, doing a bunch of research on image-based rendering or image-based realities. And some of that work actually has some very interesting implications on the graphics platform itself, especially in the media integration layer of Avalon. And so we are doing some work in prototyping some concepts for them as well, jointly with other groups. Now, this is the rough talk agenda. There's a lot of stuff. I will actually stop pretty soon, and I'll wear a different hat for a minute, and then I'll stop. And then various people will come up and talk about their projects. And before I move on, I want to say one thing. The projects that we are doing is, as is typical of a lot of what's going on in MSR, is done in collaboration with many, many other groups in MSR. It's hard for me to name all of them because I'm likely to miss someone. But just to give you some examples, we are working with people in MSR China and MSR Cambridge. But here we work with the signal processing group, the distributed meetings project, for example. We are working a lot with the graphics group, and so on and so on. So if I didn't mention any, it doesn't mean we're not working with them. So what I'm going to do at this point is go through these list of topics which cover different aspects of our work. And I will talk about the first one. This is something that has been done by David Salison, Chuck Jacobs, and Wilmot Lee, who was their intern last summer, and who's actually coming back as an intern. And since David is not able to be here today, I'm actually going to wear the David Salison hat, something I always want to do in my life, and give this portion of the talk. If you look at the state of the art in terms of reading experiences of documents, for example, web pages of newspapers or magazines and so on, this is not okay. Today, I think the New York Times headline looks a little bit more fancy. It has the nice, Gothic script and things like that. But by and large, it's really an ordered list of things, and you can click on the list, and perhaps go somewhere. I mean, this is not live, so it won't go anywhere. But it looks pretty pathetic. But worse still is that if I start changing my window size, expanding it a little bit or contracting it a little bit, what I find is that it's not at all sensitive. I get this blank white space, or I get stuff cut off, and it doesn't know that the content should be relayed. Now compare this with the real thing. This is the paper that you go out and buy in the newsstand. It's laid out so that it has some notion of how people are capable of reading. The column widths are not too large, just the right size. Photos are arranged just in the right place to make things come out, paginated and aligned right. Now, there is no fundamental reason why we cannot achieve that in our online experiences. But it takes actually a couple of steps in order to get there. One of them is that, in fact, when we have different sizes, there's always going to be an issue. What happens if it gets too small or too big? So you want to allow the author to provide multiple representations of the content itself. and meaning, maybe different resolutions and sizes of the picture, different summarized versions of the content that could be used for smaller or larger layout settings, right? But then we also, on the rendering side, we want to be able to choose the content properly based on, these different representations, and render them just so that it looks right on the particular page, on the particular layout size and things of that sort. So I'm going to switch to a demo. So what you're seeing here is a little bit cut off, I think, at the bottom, but still should give you an idea. There are actually 4 windows. This is the same content that we are showing at 4 different sort of window sizes. On top, what you see here is that, if we had this kind of a rectangular window, it columnizes into 2 columns with a certain column width, and the picture goes of a certain size over there. But as we broaden the window, it automatically relays out into multiple columns so that the columns are not too wide, no blank spaces, and it uses a different picture in order to convey the information better. In fact, I can pick up, I believe, one of these windows and move it, and you'll see it change as I change the window size. Let me close this up. So I think, notice how the different pictures are chosen and put in different places, just so that the overall layout begins to look nice. Of course, layout is more or less a science. There's a lot of rules that publishers know about and use, and really what we are trying to do is to codify some of those things into programs that would automatically use the right set of rules and behavior in order to achieve the right representations. Okay. This work is actually currently in heavy discussions with the eDocs group on how we can push it out into the Longhorn Blackcomb timeframe into their Avalon reading framework. Okay. Now the second part of, yeah.
How much burden of authoring is there to get what you were showing?
So there is, for the particular examples, I'll defer the question to Chuck, who's actually
so the main thing that we're adding is just this ability to have multiple versions of. So in that case, there are two instances of that picture. Right? There was like the wide picture, and then we cropped it into the smaller. That there wasn't very much. It sort of depends on how much you want your document to adapt to.
Yeah, so the recolumnizing is automatic, but the choice of which picture to use is based on it. Yeah.
Is there any look at automatically cropping and requiring the author to crop on the project?
That's a kind of an open question. I mean, that's what we would eventually get to, but I think that's a fairly sensitive issue with respect to what criteria to crop. So right now, we're not going there, but it can be, right? Once the framework is laid out, those kind of issues could be addressed. So the second topic that this team is working on, again, it's David and his crew, is on what we call adaptable animated presentations. Now, PowerPoint is great, right? It's kind of changed the world. Most of you probably read the famous New Yorker article about PowerPoint, and it dominates everywhere. And one of my favorite examples is that there is a chief minister in a state government in India who refuses to talk to his ministers unless their presentations are in PowerPoint or something like that. So it's got everywhere, right? Now there's a problem with it. You have you can do all these slides, but now of course, we made a last minute change to our talk. You got a few more slides. Now we have another version, right? And then of course we have to go give this executive talk to our director or something. It has to be, the elevator speech thing. So it has to be only 2 slides. So we have all these versions, multiple versions floating around on our disk with different names. And I'm sure most of you have done talk final, real final or something of that sort, right? The worst thing is, if I make changes to any of these versions, the other versions, right, which are allied with it, don't automatically see the changes. So I have to kind of, migrate the changes on my own and things of that sort. So this kind of led this group to think about a slightly different approach to sort of representing the content. Internally, if we are able to allow the user to maintain sort of a nonlinear representation. So you may have this kind of a slide organizations where there's a branch. You could use this version or this version. Once again, you might have branches within them and so forth, right? And at the time you are playing it, you can sort of, in fact, we can have a situation where there are 2 windows. As a speaker, I can have one window in which I see this. As the audience, you don't actually see this. You see the presentation, and I can dynamically select the paths by highlighting it or something of that sort, or clicking on it and show that, right? And in fact, this is just a little UI showing that if I were to do that, this may show up as the mainline path as opposed to the sideline path because I chose this thing. This is actually, by the way, a demo and application that's running. I don't have the demo running here, so I won't show you, but feel free to go talk to David or Chuck about this. Yeah?
The organization will work, but about content presentation, what's the problem that hit the world with word processing where people would drop a 100-page thesis to a 20-page article? It was totally unreadable because all the references were dangling.
Right. So, ultimately, the user can shoot themselves in the foot when you give them more kind of, flexibility, right? I'm not sure fundamentally we can change that, but we can, as we evolve this, anticipate some of the common sensical sort of things that people would want to do and make them easier to do than other things, for example, right? So this is just to show that, authoring this shouldn't be very hard. If I had to create this huge tree, and they actually have a simple UI for authoring. You can lay out your slides and start drawing, moving things around a little bit on this page and start, drawing these links and arrows, and it creates a tree structure. So it's a little bit like the slide view, a slide sorter view in PowerPoint now, but it's a different layout and with a UI for, being able to create these kind of tree structures or graph structures in the presentation. Now, adapting in terms of layout, in terms of which version to show is one half of the story. But animation is one of the great things PowerPoint enable. But most of us use animation as in a gratuitous sort of way, right? It's basically for having fancy flying bullets. But really, animation should be actually to convey a concept where animation makes sense. So for instance, if I want to tell a story about, showing the effect of changing, the dynamic of this pulley system, I'd like to have a control which I move around and actually something happens. And be able to author it and tell this kind of a story. Or in fact, I may want to script it and say, move it at this sort of a speed and it plays itself later, right? Now, what I'm showing here is a system that David and his colleagues actually more at UW have developed. This is a presentation that they put together based on the system that they developed. And this is a proof of a Pythagoras theorem. If you can't figure out what it is, from the picture itself, you have to go back and do your homework. I'm not going to tell you. But this is a different example of, how the same system for making animated presentations can be, used to talk about pointer passing in C++. Or something else, something which is more like a graphical layout and how, the different arrangements can be done and things of that sort, right? So this is something that's kind of an ongoing work. The basic idea is to create sort of a scripting language and an interface for creating presentations, and then a playback, of course, that will play it in the proper way. We are talking to the Sparkle group, which is a natural place in the company for this kind of stuff, about potentially, migrating this. And okay, so at this point, I'm going to switch over and ask David Bargeron to talk about his stuff.
Hear me? Am I on? Okay. So, hi, I'm Dave Bargeron, and I deal with multimedia annotation issues in our group. And we kind of follow two broad directions in this work. One is to look at end user scenarios supporting personal annotation on documents or media objects like video or images. Or collaborative scenarios where you have multiple people collaborating either synchronously or asynchronously around documents and video. And then the other broad direction is once annotations or metadata exist, what do you do with it? It's useful when you've got annotation. I'm sure you've all had this experience of flipping through a used textbook and you see the parts that have been highlighted or annotated by other people or by you earlier. And so that's kind of an indication of the important parts of that book. Well, that same idea extends to web pages and videos and stuff. So that's the other major direction. Most recently, I've been working on ink annotations for reflowable, modifiable documents, and I'll talk about that toward the end. First, though, I'd like to talk about the Common Annotation Framework, which Anandan mentioned. This is a project that we've been working on with a lot of different product groups. I need to click this thing. Okay. And the idea behind it is to create a platform for support of annotations across Microsoft products, a common, consistent platform that people can use. It's composed of a schema and an object model. The schema kind of defines what an annotation is, how it's structured, what you can do with it. And then the object model provides a consistent layer that you can use to manipulate annotations in applications. And the underlying idea is basically that annotations are links between two pieces of content, or a link between the context of an annotation, that is where the annotation belongs in the document, for instance, and the content of the annotation, the comment that you made or spoke or something like that. Broadly, our design goals here were to create a lightweight but extensible platform that would be storage neutral, to allow annotations to be stored in a variety of different ways, either in a document that's being annotated or separate from it, so that they can be shared. We wanted to support annotating any media type with any other media type. And we wanted ultimately to kind of foster a more consistent user experience for annotations across products. So if I annotate a web page or a paragraph in a web page and I copy that paragraph and then paste it into an Outlook email, the annotations that I created in IE should follow to Outlook. Today, they don't do that. The Common Annotation Framework version 1.0 schema is currently being used in WordML, which is being developed by the Office team. That effort is being led by the Authoring Services team, and basically that schema will support revisions and comments and other annotation features in Word. So in addition to kind of the theoretical and product work that we've been doing, we've also developed several research prototypes that I'd just like to talk a little bit about now. This work was all done by AJ Brush, who was an intern with me for the last couple of years. This is kind of a prototype to support shared or personal annotation on web pages. Here, the different colors indicate different authors. So you can see that there's a bunch of different people making comments on the web page. The web page is on the right-hand side. And on the left-hand side, we've got an index of all the annotations that were created on the page. So I can click in the left-hand index on an annotation that looks interesting, and it'll navigate me to the right place in the page. By extension, you could have annotations from a variety of different pages listed there. Click on one, and it would actually navigate you through the web to that page. And vice versa. When you look at the annotations on the web page, it'll take you back. These annotations we sort of experimented with two basic levels of access. One was private, and the other was public, so that everybody could see them. And we also looked at supporting annotations with robust anchors, meaning that when you annotate a web page, the web pages often change. So if I annotate it today and then I come back tomorrow and the web page has been modified, what happens to my annotation? Of course, web pages are read-only, so you want to store the annotation separately. So you need to store enough information for the annotation to be able to keep up with where it belongs in the web page, even if the web page gets modified. So that was the kind of goal of that work. Something a bit more applicable to today's talks is video annotation. Here we've got, actually, let me start this up, and because this makes more sense when it's live. Oops. Well, we won't do that. So the basic idea is you've got talking head video and synchronized slides and table of contents. That's something that you can get with PowerPoint today. You've been able to do that for years with PowerPoint. But in addition to these, which are implemented as annotations on the video stream, you've also got a seamless method for drawing in people into a shared discussion. So this is what we're looking at here. Anybody that comes to this web page can watch the video, and if they've got a question about what the speaker is saying or what's going on in the video, they can ask a question. Somebody else comes along and perhaps knows the answer. They can reply to the annotation that was created earlier and put in the answer. And so you get this growth of threaded discussions all centered in the appropriate places on the timeline of the video. In addition, you can have a private notebook for each person that comes along. So if this is a college course, for instance, and as you're watching the video, you can be taking notes on what the lecturer is saying. Okay, so that was all based on version 1.0 of Common Annotation Framework. We're working on 2.0 now, and the idea here is to make CAF .NET compatible and to strengthen the typing mechanism in schema. The earlier version 1.0 schema was rather loose. and also to provide a UI component framework that will kind of enable an even more consistent user experience across applications. This work is being done in close collaboration with the active reading team, including Axel Kramer, Kathy Marshall, and Ralph Ruiz. And then we're also integrating it into the Avalon platform, and that's led by the Avalon and eDocs teams. The neat thing about the Avalon integration is that applications that are created on the Avalon platform will just sort of get annotation functionality for free right out of the box without doing much more than flipping a flag. And then in addition to that, applications that are not built on Avalon, for instance, on Win32 or something, will still be able to avail themselves of Avalon annotation platform facilities. Okay, so that's CAF stuff. More recently, I've been working on, as I mentioned before, ink annotations for reflowable, modifiable documents. The idea here is to give people the ability to annotate digital documents, and by extension other media types like photographs or video, in the same natural way that you can pick up a piece of paper and a pen and start drawing on it. And these three pictures, I hope you can see them, kind of illustrate the idea. If you ink over a web page, at one particular window size, and then the window size suddenly changes and all the content and the layout reflows on that page, you need to have the ink kind of catch up with and adjust so that it makes sense in the new layout. So here, this 2-line underline became a 1-line underline, and this connector arrow was kind of squished up. And then also, if the layout changes again to be more narrow, you have to make adjustments there as well. The same kind of thing happens when the document is modified. That precipitates layout changes as well. The algorithm that we're following follows 3 basic steps. First of all, we need to group and classify ink strokes as the user is making them on the web page as to roughly what they are. Are they an underline, part of an underline, or are they a circle or a margin comment or a connector arrow or a bracket or something like that? And then once we've made that basic decision, then anchoring the ink to the underlying document. And then when the document reflows, we need to reflow the ink in a smart way as well. So there's a lot more to do in this area, and I won't go into detail, but as I mentioned, the direct ink on video annotation stuff is kind of exciting, and we're looking forward to working on that. And as with the other projects, I've been working with lots of different people, both here in MSR Redmond, including Patrice and Michael Schillman, some folks from MSR Beijing, and then the Rich Ink team and others from the Tablet PC group as well. So that's multimedia annotation. Okay. And then go that way. So I'll hand it off to Kentaro.
Okay, so hi, so I'm Kentaro Toyama, and I'll be talking to you about video cliplets. Most of this is going to be a demo that I actually showed at TechFest, so it might be a repeat for some of you who've already seen it. So we have a lot. This is a very large team project, including people from MSR Cambridge here and using some technology from MSR Asia as well. And let me just jump right into the demo. So our goal with this is to basically provide an alternative, a simpler alternative for playing with video, as opposed to what currently happens in the shell, where you see a single file entity for every captured video that you upload from tape. Now, the idea with cliplets is simply that instead of assuming that the file is the atomic unit of video, we're going to assume that these short little segments of video that we call cliplets are the atomic units of video. And so that's what you see here. This is a 5-minute video, which otherwise might have been represented by a single thumbnail image in the shell view. This is our mock-up of the shell, and you can see that they've been segmented into a whole bunch of different cliplets. And we do some intelligent processing to make sure that we try not to cut people off mid-sentence. We respect all the shot boundaries that are in the original movie. We respect certain boundaries that aren't shot boundaries, but which have been determined based on scene clustering that you'll hear about later. And these cliplets play in place. and so on. And you can see that, for one thing, you get a much better sense for what's contained in the entire tape just at a single glance than you would otherwise. Now, a lot of people have told me, well, if you have an hour of video, that's going to be at least hundreds of cliplets. And the answer is yes, that's true. But the alternative is to see one thumbnail for the entire tape. So this is at least you get a much better sense for what's contained. And this is actually the analogy here is to make video as close to photos as possible. People already understand how to use photos. They understand what they want to do with photos, and so we want to unify that that's the stream of thinking that people go through with photos, starting with capture all the way to creating photo albums, and we want to duplicate that for video. So during the processing of the cliplets, we also do certain other kinds of processing. So for example, we use MSR Asia's face detector and then create a facial prominence score per cliplet. And I've now sorted that based on facial prominence. So you can see that at the top, you see a lot of faces. And as you go down, there are fewer and fewer faces in the videos. Similarly, we can do one for audio rating. And here you get a lot of excited speech being prominent at the top, and whereas background noise and other less interesting sounds appear at the bottom. Okay, so going back to time. The other thing about this is that it creates a better unit for doing all sorts of video processing. So, for example, video stabilization is something that people often talk about, and it's something that is applicable to video as a whole. But again, it's very unlikely that you'd want to run stabilization on the entire video as it comes in. So one thing we can do is we can say, okay, well, I just want to look at it for a particular section. So here what you see on the left is the original jerky video, and on the right the enhanced version. And this is technology that Andreas will talk about next. But the idea is to provide a UI such that you do the stabilization on the cliplet in the same way that you might do orientation correction on a photo. Okay. Another thing we can do is, for example, change the aspect ratio. So again, just like you could crop a photo, you can change the aspect ratio of a cliplet. This is a scene of a woman walking on a beach. And I'm not going to show you the tracking UI, but basically we can create a version where the aspect ratio has been changed and the woman remains in the center of the movie. Or if you want scenes like this and want to see them in slow motion, then we can also do the processing to do a frame interpolated version. And this is 2 times or 4 times the original video in length, but it's got as many frames per second. Okay, so let me move on to what do you do with this. So again, this is what we want the shell to look like, and actually we've been working very closely with the Shell MSX team, and they've taken this much further and already created several versions of this that take this idea and run with it a little bit further. Now, basically, because we have these cliplets as entities, it means that video editing no longer has to be about scrubbing on a timeline. It's no longer this really, really tedious process that even professional trained video editors have to go through just to create a single movie. So over here, we have what we call the cliplet collage. And this is in response to the tendency for everybody to think of video as always being this linear thing that you watch on TV. So instead of authoring another video out of your raw footage, you can create a collage. So you can drag and drop. These guys, of course, play in place. We can add text annotations to them. We can split up the screens and so forth, so you get a different view of a thumbnail. And because of all the ratings that we have on each of these cliplets, we can actually populate these automatically. And in some sense, this is the highlight video created from the original cliplet. This isn't doing a duplication rejection, so some of these are duplicates. And of course, if you don't like something, you can always overwrite it, and so on. So this the authoring process becomes much more simple. It's much simpler than having to edit a video and so on. Now, you can also add things like title, cast, background photo, background music, and that gives you something like this, where, of course, each of these plays on click. And you can imagine this could be the document that you send to your grandparents instead of an edited movie. This could be the thing that you use as the DVD chapter page. It could be a web page that you ship out, and so on. Okay, and finally, there are people who always insist on having a single video out of this. So you could easily take these, time order them, add the titling, and so on, and that would give you a single movie. So that's it for the demo. Okay, so we've been so the reason why this demo is actually exactly the same is that we're sort of in another incubation period, and we're working on a version of this demo that's a beta, and Steve Harris has basically gutted the original demo, and so we're in the process of rebuilding. And the second version will actually hopefully be connected to a database so that you'll actually be able to do interesting queries on video. The interesting thing about video and querying is that more often than not, you'll want to query into portions of the video. So it's no longer going to be a query over files. It'll be a query over cliplets or a query over subsequences. And so that presents some interesting challenges, especially for the operating system if we can convince them to go in that direction. The other things we're working on are metadata schemas for video and also versioning policies for video. Versioning I think it's a manageable problem for video. It's a very hairy problem in general, but it's manageable for video largely because people are much, much less likely to actually edit the video bits themselves. They may modify them a little bit, they may enhance them, but they're not likely to modify them in the same way that they modify a document. We're also, a lot of our concentration is actually on the UI, so how queries are made by the user. I mean, probably users don't want to know that they're doing a query, but we want to present it in a way that they have an intuitive understanding of what they're searching for, and also for an intuitive way to display those query results. And recently we were working quite closely with the Windows Shell team, who's working on several iterations of a UX demo, and also with the Movie Maker and the Movie Maker team, which is concentrating largely on video. And we anticipate a lot more interaction in the future with the Windows the Future Storage team, which used to be called WinDB or Mighty Mouse. Media Foundations, which is the next version of, or the evolved version of DirectShow, which is what's underlying the current demo. And also the Digital Memory Project, which recently was absorbed by WinFS. And that's it for me.
So I'm going to talk about enhancing consumer video. Now, when you think about our own personal home videos, we're experts at watching television shows and movies, and they're all nice and produced, and they look great. When we look at our own home video, they look terrible. And a lot of the common flaws that exist are things like there's always camera shake, there's noise coming from the CCD camera, there's all kinds of interlacing artifacts, color balance issues, out of focus. These are the type of problems that we're interested in solving in our video enhancement framework. And so I'll jump right into it and say that we really want to solve only one-click automated solutions to these with no user interface. Keep the user out of the pipeline, just make it work. So jumping right into stabilization, this is an example of typical home video. You can see it's really shaky and really contributes to making the video look very cheap, very unprofessional looking. Now, at the heart of solving this problem, we have what's called an image registration algorithm where we analyze successive pairs of images and we compute what is the aligning transformation between these two images. So here, unless there's an earthquake in Seattle, we know that the Space Needle doesn't rotate, so there is a transformation that can align one frame to the other frame, and we solve for that transformation. It's a minimization problem. And once we solve for that transformation, then we unapply the camera's transformation, and we end up with two images that look very similar to one another. So we've undone what the camera's motion did. So having said that, this is, again, the original example. You can see there's a lot of camera shake, and there's a lot of rotation as well. And this is what the stabilization algorithm does. You can see it's moving it's warping the image in a direction opposite to the way that the camera moves, so the content stays more or less in the center. Now, you notice all these unpleasant artifacts in the borders. What we can do is we can stitch together the missing pixels by stealing them from nearby frames, and you end up with something that looks like this. Now, there are some artifacts on the side because the registration is just hard to do around there, but it is much more pleasant to look at than the original. Moving forward, like I said, a lot of cameras offer have a lot of bad CCD noise in them we want to clean up. So we want to clean up the noise but keep the video looking very sharp. And the way we do this is we turn to temporal filtering, where we stack up the images as acetates in time, and then we filter along the time axis. But what we want to do is we don't just want to filter blindly along the time axis. We actually want to warp every image along what are called optic flow vectors towards a center image. And let me give you an illustration of that. Basically, the way it works is you line them up as acetates, and you notice that the eye has moved at different locations at every frame, and you filter along the optic flow trajectory. So the optic flow tells you how pixels move. Filtering along those flow trajectories gives you something like this. Now, if you do an alignment, this is a frame of 17 frames, and this is everybody in that neighborhood of frames aligned towards the center frame. So what we do is we first align towards the center frame, and then we filter in time, so that we've sort of canceled out the motion. But you notice there are artifacts here, like where my mouse is and where the horizontal blinds are. So we have some robust metrics that can figure out what to do and the right thing, what the right thing to do is there. So this is the original, and you can see it's very noisy. And if I stop that and I show you the denoised result, you get this. And the details are preserved while the images look nice and smooth with no noise. Now, slow motion is something that users want to do. They want to capture the moment when their son hits a home run on their Little League video game or something like that and slow it down. So let's say you want to slow down this video. An obvious solution would be to repeat frames, and you get the bottom left here. That gives the jerky robot-like motion. You may want to try frame averaging instead, but that gives you this ghosting type of effect where you get sort of like this double vision, as you can see right here when I pause it. It just doesn't look very nice. The right thing to do is to interpolate in space as well. So in order to do that, we need to understand how pixels move in space. So we compute the optic flow field, which tells us how every pixel moves, and then we warp images forward. Yes?
Did you get that from the MoComp in the stream?
The vectors in the stream are coarse. They're very sparse, and they use crude block matching techniques, which are not accurate enough for this type of, and it's not dense correspondences. And this is the actual slow motion with optic flow version. So you can see it's very crisp and smooth, and her hair remains nice and sharp, and his face remains very nice and sharp. So we can use optic flow as well to extract the still from interlaced video. Again, this is one of the problems that plagues consumer video. So this is just a cliplet of interlaced video just played back and forth very quickly. Unfortunately, because I've rescaled the picture, PowerPoint is munging the odd and even scan lines in a strange way to use these artifacts. But if you want to extract the still from this video, well, this is what it actually looks like in memory. I mean, the video is you have one even field, one odd field, one even, one odd, and they're half red. So if you play them back, you end up with something clean like this, but you need to scale up and generate a full frame from these fields. So the way to do this is to if you're at, let's say, frame time 2/60, and you want to interpolate the odd field, well, you can again use optic flow to warp an odd field into place, and then you generate a full frame. And this is what the result looks like. So you go from this is the interlaced, and this is the deinterlaced frame, and you get that. And as you can see, it's very, very sharp. So in terms of technology transfer paths, we have real-time stabilization that we're working on with Movie Maker, and we will hopefully get that into the Longhorn shell as well. So you'll be able to right-click on a thumbnail in the My Videos folder and click Stabilize. Real-time optic flow, and we really want to push towards having motion information available everywhere, tagged along with the video cliplet as metadata, and slow motion and high-resolution still extraction. And also, I just want to show, so I've been working with the Windows Media Codec group, and in particular Simon Winder, who's written a really cool piece of code to do quick registration of images. And this is the original. This is D-Show, so you can see this is all happening in real time. So this is the original.
The video overlay's messing up on you. Your screen's blank.
Okay, well.
Don't show it on the laptop, only on the screen, then it'll be okay.
Blank your screen, your
see.
laptop screen. There you go.
Okay, so. Okay, so this is the original video. And now what I'll do is I'll close that, and I will hit delete. And now pass it into the stabilizer filter that we have. Yay! And these are preliminary results. So you can see this is happening in real time, and this is making call into the Windows Media Player team's code, Simon Winder's code. And he's got some really cool MMX routines to do some of the registration. So that's it. Thank you.
Can you switch the computer? Okay. Wait. Okay, about that. Yeah. So thank you. So I'm going to just sort of keep in time. If this were a Bollywood movie, you would have an intermission by now and go, drink coffee or smoke cigarettes, but we don't have time for that. So I'm going to go quickly so that Rick, and the team can have their full 15 minutes to show the most cool stuff you'll see in the end. So we're going to keep the best stuff for the last. Okay, so as I said, the other aspect of our work, which is Nebojša Jojic, which, to do that, I'll have to put a thick Serbian accent. I don't think I can. But, working on video understanding side of problems. He has a whole lot of collaborators. And the overall goal is basically to do everything. He's quite ambitious. He wants to find objects and things in the video, how the video is formed, how objects are changing their appearance, the motion information, any other higher level properties. And want to do it in a way that, everything is done automatically with no initialization, no hidden magic numbers and such. But the framework that he's using is kind of widely popular in the machine learning community and applied to a large class of problems these days, and lately applied to multimedia, audio, and video. And we have actually a bunch of people at MSR working on these type of problems. And Nebojša's slant on this is on video understanding. Basically, it uses a framework called generative density model. Basically, you specify as a developer or an engineer how the data is constructed from some whatever abstract concepts and models. But these are all specified in a probabilistic framework such everything that is done, everything that you compute and estimate is actually a probability distribution over some set of variables. And so that allows you, to deal with a lot of variability and noise and things of that sort. As well as when there's indeterminacy in data, it doesn't come to the wrong conclusion. It simply says that there is indeterminacy of data and doesn't, gives you a distribution over the possible set of conclusions. And he's got several things going, and I'm going to just quickly focus on two things. One set of models that he called transformed mixtures of Gaussians. Don't worry about what that means. And the other one, which is about a layered representation of video sprites. Now, the first thing this video illustrates that. This is the input video at the bottom, and what he's doing is automatically detecting that there are 5 different facial poses in this one video, and has learned this from just analyzing this video. So what you see up there is the class index generated by a system, which is changing over time, saying that it's not right now pose 1 or pose 3 or pose 2 or whatever is playing, and this gives you the mean image associated with that particular pose class, if you will. And of course, it has had some variability here, and here now you begin to see just to show that this thing can handle, partial information. So he's kind of blacked out an area that's not an issue for the algorithm. And this shows the kind of transformation, spatial transformation of the object that's taking place within the image, and then the whole thing is combined to form the final video itself, right? And there's a slightly different demo of the same thing, which I want to show you in a moment. This is the same video that Kentaro was showing earlier. This was the original video we shot in Hawaii. This is the input. I will not go through all of it, but simply show you the demo associated with this. So this is actually a MATLAB demo. So it's not, it's not ready for production or something like that, but it gives you an idea. He specifies that, say, let's say there are 15 different classes, and this is a user-specified number in this case, that are there in this video, and the system has decided to divide this long video into this set of 15 classes based on things that are distinct from each other and variables. Sometimes the same object, for instance, might be in 2 different classes. There may be, I don't have control over my mouse, so I can't show you. I think there are 2 different David Salison faces up here corresponding to 2 different zoomed resolutions. So it's got, a little bit of redundancy there. But the interesting thing is that if I start now playing it and I press this enter button, you'll see the laptop. Oh, right. That's why I did it. Thank you. It helps to be on the right machine. Okay. So, yeah, if I play the enter button, what you'll see is in this window, you'll see a red line. This is a class index over time. So it's showing which class is playing. Bottom here is the frame that's currently played, and here is the mean representation of the class. Notice that the mean is not very accurate because there's a lot of blurring because of movement going on. But it gets the right class, as you'll see in a minute. And if I keep pressing it, as the video evolves, as the frame changes, now a different person comes in, it changes the class according to that. And then, as the conversation goes back to the previous person, you'll see in a minute that it switches back to their class. So this is something that the system has automatically decided that these different segments and frames of the video are to be associated with these different class indices that it has learned. And what you being shown is just 2 different displays of the same kind of information. So now it's gone back to I think this is Colin Davidson, a friend of ours. And I'll just go a little bit more, because I want to show you something more than Sumit and Colin. And you'll see in a moment that there is a little bit of the baby. So this is, 2 different classes associated with the baby because of the 2 different zooms and things like that. So I won't, spend more time on this. Now these multiple classes are the same thing, by the way. Right now, as I said, we haven't really tried to make an attempt to, to come up with the minimum number of classes and so forth. But, it's a good starting point, right? Now, this is more fun. Oh, this is because I was randomly pressing this when I was playing the other demo, right? The other idea that Nebosha and this, and this team are working on is this notion of actually decomposing a video of multiple objects into what we call different layered sprites. And those of you who've been around long enough, with PhotoDraw and so on, know what sprites are. But here they are animated sprites. And here's, we play a video. My link may be broken. Okay, let me just go back to that and see if I can play that. Otherwise, it won't have the time on. Okay, for some reason, I guess my link. Don't worry about that. So here's an example of the same thing. What you see is, again, the final, this is the input video. And it's been, determined to have one background, layer, which kind of consists of the entire background, and then a person moving in the foreground whose appearance is modeled in terms of the mean and the variance here. The masks indicate, what spatial support associated with the different layers are. Like the background, doesn't. This is actually a, white mask. That's why you don't see it because it's the entire background. And the position variable indicates where the particular layer is with respect to the rest of the image. And this sort of is a compositing graph that shows you how the video might have been generated from these inputs. But what in the end actually happened was that the input was given and these intermediate things that we are showing were produced by the algorithm. And of course, now once we have these layers, we can also do things like stop the person from moving by controlling the position variable and make it look like they're walking on a treadmill. Or we can actually flip them backwards and have them, walk in the opposite direction. These are just some, just some little cool things. Or we can make them moonwalk, right? Because after all, the video shows them moving forward, but we can move the time variable. We can send the position variable backwards, and then it looks like they're moonwalking. So this just jazz. And this is another example of the same approach. Now, with these 2 things, it's divided the scene into 3 layers, 1 background and 2 objects, and we can do, stabilization without Andreas' help, for example, by holding the position of a particular variable constant, or we can actually remove them and render the background. Right? So this kind of things. Okay. And of course, this is from the New Yorker. I'm one great believer in layered representations, but New Yorker is ahead of me, and this cartoon explained why we need to have layered representations in the first place. Okay. These are some comparisons to various other things. The main point here is that some of these things are surprisingly fast. That this stuff that I showed you about clustering can actually happen at much more than 1 frame a second, but it's still not at real time, but it's pretty close there. And we are actually working on turning these clustering work into a D-show filter to take advantage of some of the acceleration capabilities there, as well as the MMX code and so forth. And these are things that Nebojsa is doing, again, jointly in contact with the Movie Maker team. And the last 2 things are other projects he's working on, which I won't talk about. Okay. Now,
start with a quick demo, which we'll jump right to the chase, show the demo, and then Rick will explain how we did this. Second to load. So this is again our TechFest demo. For those of you who've already seen it, I apologize. But here I'm showing a completely interactive experience that you'd expect from something like a computer game. I'm controlling it.
You better put on your earbuds.
Okay, I'll talk into here. So I'm showing a completely interactive experience that you'd expect from something like a computer game, except I'm controlling. This is all based on real imagery. So I'm wandering around this house under control of this gamepad, and you can look up, down, all around. And in addition, we've placed some interactive elements in this scene. So again, the Baywatch video shows up. And also we've got a little fireplace going there to add some ambiance. But I can walk all around the ground floor of the house here, all interactively. And if anybody wants to try this out after the talk, you're free to come up and play with the joystick. So I think Rick will explain how we did this.
Okay, thank you, Matt.
No problem. Where's the... Okay.
yeah.
This one. Yeah. Okay. So this work that Matt just showed you is part of is being done by the Image-Based Realities team, which is Matt, Singbin Kang, Antonio Criminisi, myself, and Anandan. And this is a project we started about a year ago. And the sort of high-level question we're trying to answer is there some kind of a true convergence between 2 different media types? So if you think of computer games, which are very interactive but are still look synthetic, and if you think of video, which is very realistic and has a strong narrative, is there some merger of that? So the goal of the project is to try to investigate what this kind of convergence might look like. So can we develop a new medium that somehow combines the interactivity of video games with the realism and the narrative that you have with traditional video? And the first demo we're working towards is what you just saw. So we're going to start with a real world, with somebody's home, maybe eventually a historic site or something like that. We're going to capture it using some novel technology. And then we're going to reauthor it in such a way that it becomes much more interactive. So the person can traverse this space. They can interact with particular objects. They can maybe do remodeling and things like that. And we're trying to demonstrate that this kind of thing is doable on today's PC, and that also there are new things we have to add to the platform to support this more easily. So the whole process of creating one of these interactive videos looks as follows. We have to start with data capture, and we have a novel sensor I'll show you, and that gets streamed to disk. Then we have to do some pre-processing, either before or after the capture phase, where we have to figure out how our sensor is calibrated. Then we have to take all of the original video and stitch it together into a big sort of 360 video. And as well, if we're going to do things like object replacement, like where you saw we inserted the synthetic TV show, we have to do some tracking. And finally, we have to compress this. This is a data stream that has many different video streams in it, and so we have to be very clever about the compression. And lastly, there's the viewer, which was what Matt was running, that somehow decompresses the appropriate data, shows you the correct three-dimensional sort of view of what you're looking at, plays the related embedded objects, and does all of that interactively. So let me tell you just a little bit about each of these steps. The hardware we're using is a special head that looks like this. It basically has 6 cameras arranged in a circle and one looking up. And you can mount it on a tripod if you want, like over here on the right. The head itself was built for us by a small outfit in Vancouver called Point Grey Research. They call it the Ladybug. And it actually streams directly over fiber optics to a set of striped disk arrays. The disk arrays and the power supply are small enough, they're about a book-sized unit, so the whole thing can be backpacked if you want to. We're using high-definition cameras. We're not using standard cameras. Each camera has a very wide field of view, and we can get 20 frames per second out of this. So it's a very high-end version of what you may have seen in another context. The collaborative meetings group has a real-time version that they can use for video conferencing. This is the offline version meant more for production quality filming. Now, there are some problems with the camera, the way it comes in. Because we're using very wide-angle field of view lenses, images aren't rectilinear. So we have to figure out how to straighten things out so that parallel lines meet infinity. And we do that using a fairly simple parametric model. We basically have to estimate the focal length for each camera, figure out how to straighten all the straight lines, and then figure out how these various cameras are arranged relative to each other in terms of rotations. So we do that using some image stitching software that we've developed before. Another problem that happens with wide field of view lenses is an effect called vignetting, where if you look in the corners of the scene, it looks darker than the middle. After you undo the vignetting, the whole image looks properly exposed. So we do that by basically taking an image of a neutral color, then fitting a particular function, and then everything is flat. So we're doing both photometric correction, which is this vignetting, and geometric correction, which is the unwarping. Then we have to take these 6 video streams and somehow stitch them together. And the video streams overlap. This is on purpose by design. But in the overlap regions, we somehow have to blend things together in a way that doesn't show any seams. Now, if we just do this by averaging things in the middle, then we end up with problems like this. This is basically a kind of double imaging, which occurs because the cameras aren't actually mounted right on top of each other. There's a slight distance between them, so the closer in you are, the more parallax there is, and that causes double imaging. So Singling developed this algorithm, which is called the multi-perspective plane sweep. It's a generalization of a classical stereo matching algorithm, and we apply this pairwise to all of the overlapping regions between the images, and then we blend the cameras, the colors. So without this multi-perspective plane sweep, we have this kind of double imaging. After we've done it, we get a nice sharp image. Again, here it's blurred, and here it's sharp. So that's sort of our secret technology for making the stitching very high quality. Another thing we have to deal with is stabilization. Because the camera is being pushed along by a person, or it may be very irregular. And this is basically a variant on what Andreas was showing for stabilization. We do it with all of our cameras together, and we basically figure out what the camera jitter is and then undo it at the final player stage. So that's stabilization. Now, if we want to, we can add synthetic elements to the video. So if we put in this kind of a blue screen target in the video, that's what it looks like originally. This is just camera motion here, handheld camera motion. We can superimpose a still image in that same place. We basically track what's going on in the left image and then do a superposition. We also have to know which pixels are in front of the object, so we use some blue screen technology. And if you do this with video, there's the original video, and now when we add the synthetic video, and Matt tells me that the data rates pumping through our system are sufficient that you could actually take video captured on your PC, just streaming in off the airwaves, and insert it into this sort of a scene. So there's some special tricks using DShow and Direct3D to make sure this all works. But basically, today's PCs are beefy enough to do this kind of video insertion into synthetic scenes in real time. Okay, so what is the magic that then takes all of this pre-authored software and lets it run in real time? It's a piece of software developed by Matt called the Research Media Viewer, which is a very clever combination of Direct3D and Direct Show, and it also uses an XML scene graph to tie all of these media types together. Our actual model at the moment is just 6 texture mapped videos. So we basically transmit or compress all of the 6 videos together. Each one of them gets projected onto a plane inside a 3D world, and then they're rendered using D3D. And Matt has added new techniques, new software to do selective decompression, because we can't afford to decompress all of the video and do the joystick control and those video overlays. So for selective decompression, we notice that at most in any one view, we'll see 4 of the videos. So we take the videos, break them up into tiles, and then we decompress each of the tiles that needs to be shown, but none of the other ones. So that limits the data rates. It also limits the amount of video that we're pumping into the texture memory. So everything is matched carefully for the hardware. We saw the demo. So I think at this point, I'm just going to move into future work. So we have more work to be done in camera calibration. Basically, we have to determine where the camera centers are relative to each other in a precise way. And we have a lot more work to be done in scene modeling. You may not have noticed this in the original demo, but if you looked outside the windows, everything was washed out. If you looked in the dark corners, everything was dark. So we're going to be taking images at multiple exposures to fix that. We also have to fix missing data underneath the camera, and we want to do better object insertion and eventually some sort of directional sound. I'll show you a little bit more details on these in a second. Another big issue is compression, and this is related to a more general open problem, technical problem, as to how to do good compression of light fields for image-based rendering. And then finally, Matt is working hard on porting this to the .NET architecture, and directional sound really belongs here. So let me show you a little bit more about these various parts. Here's what you can do if you take 2 different images. This one's underexposed in general, which means that the background, the house there, shows up well. If you overexpose it, so to speak, the inside, the piano, shows up just fine. And if you combine this in an intelligent way, you can get the outside house and the piano both properly exposed. So these kinds of techniques have been published in SIGGRAPH in the last few years. It's a very popular area. And we basically want to take this and extend it to moving images, video. This is something no one has ever attempted before, because what we're going to be doing is taking a dark image followed by a light image followed by a dark image in a moving scene. So we're going to have to apply some kind of optical flow, like what Andreas was talking about, and then combine the images in an intelligent fashion. But I think this will give us a big benefit for our application and could even be used for other commercial video production. This is something that could potentially go into future video cameras. We have hole filling at the bottom because basically as the camera moves around inside this building, it sees the floor from different points of view. So even though you can't immediately see what's underneath you, we can fill it in from other frames. So we're working on that. And we're going to be building 3-dimensional models. The reason it's important to build 3D models is both to be able to interact with the world, like to be able to, let's say, move books around on a table to redecorate your room, but also to do better compression. Because basically, if you can tell where the geometry is in the world, you can predict how a video frame will look from one location to the next, and that will give you very high compression. So Antonio here is developing a very long feature tracker that works both on points and on straight lines, and we're going to be building 3D models based on this. So in terms of compression, this is a real interesting sort of open problem. It's a generalization of classical video compression, because we want to be able to decompress basically going forwards in time and backwards, and selective decompression is very essential for this to work. On the other hand, we know that our world, at least for the initial demos where we're filming static worlds, can be very well described by just the geometry. That completely predicts what the motion is, so we're going to take advantage of that. And if we do that correctly, we'll be able to not only compress the video, but also move to new viewpoints. So we'll be able to move off the original camera path. A lot of people who see the demo don't realize that you can only go back along the rail where the original camera was moved. But in future versions, we'd like to be able to allow people to move to locations slightly off the rail. If we have a 3D model, we can do that. And we're also going to be dealing with specularities and reflections. So in the interest of time, I'm not really going to tell you much about our work with specularities and reflections. We have some really interesting work that shows how you can decompose this kind of a light field into separate streaks for the reflections and separate streaks for the objects while accounting for occlusion. So this is ongoing research. Last thing I wanted to mention as one of the fundamental areas we're working in is in rendering architecture. The 2 primary top-level goals of this project are, one, to demonstrate that there exists a compelling visual medium that's the sort of combination of video and gaming and graphics. The second thing is to actually develop the architecture within Microsoft that will support this. So we're working basically to extend the Avalon media integration layer into 3D and video. And this is work being done joint with graphics people like Charles Loop and some others. But it's going to be a combination of XML and Smile, which is what Avalon is based on, and then with the addition of the appropriate hooks into Direct 3D and Direct Show. So we're hoping that this will both be something technology that migrates into the Avalon team, and it'll also be a new substrate to unify a lot of the image-based rendering research that's being done in our group and also in the graphics group. So the last thing I'll close with is just a couple of pictures. This is the robot cart that Xingbing has been working on to acquire the data for when we're inside a building. If we go outdoors and we want a wearable version, and Xingbing's going to stand up and model the wearable version of our acquisition device. This is a skydiver's helmet recommended to us by Barry Brummett. So it's very stable. And we can walk around. Xingbing didn't bring the backpack, but basically all of the capture hardware and power supply fits in a backpack. So you can walk around. We'll take this to the Japanese gardens or something, or maybe Pike Place Market, and get some 360 videos. So this is the future of broadcast video you're looking at right here. Okay, so wrapping up. What are the contributions? We're obviously doing interesting work in novel sensors like that. We're doing a lot of work on basic vision algorithms to be able to take that rich video data and extract the three-dimensional information in it, so we can build these kinds of virtualized worlds. We're also working on very important parts of image-based rendering. Basically, one of the big open problems is how to do efficient compression to take all of this imagery and make it transmittable. Our initial target is to be able to author things to DVD rate, so we can basically capture somebody's home and put it on DVD. In the long-term future, we're going to be looking at streaming media. And we're also hoping to make a big impact in terms of the actual Microsoft architectures at the graphics and video levels. So the ultimate goal, as I said before, is to sort of build the next generation of converged media that's a combination of graphics and video. Thanks.
Okay, thank you, Rick. So now it's time to take a deep breath. We're almost done. So this is like a Bollywood movie. We had some love scenes, some fight scenes, some whatever, and melodrama. And now it's time for a happy ending. And that's what I'm going to do. Summary, as I said in the beginning, the three factors that are impacting the future of PC. I won't repeat them. And the consequences really are for us is that not only will there be a rich visual media experience, which we are working on, but also the breakdown of the barriers between different types of media as living in different silos, different worlds, and so on, at the level of authoring, rendering, at the level of experience. And more important, I think this is our pet thing, is that all media, we think, will eventually shift towards being an interactive type of entity, interactive media. And our goal, our plan for getting there is simply to work on the technology, do good user experience to show off these technologies and motivate the technology development as well, and then work with the product groups towards changing the platform. After all, this is a platform company, and that's the best way for us to have an impact. To this end, we have actually got several sort of initiatives going. As I said, we are working jointly with the graphics and Next Media groups here, as well as the Avalon team, to be thinking about seamless media integration, this idea of graphics and imaging and 3D and 2D mixed together. The second thing is that we are also talking to some of the groups in the media division. It's WDM or DMD, I'm not sure what it's called now. But on the notion of interactive video, because the current video platform is largely optimized for a sort of a streaming and viewing experience. So if I want to treat the video as an interactive element, it's not really what it's meant to do. So I've been talking to the Media Foundation group and the AVPG group, and as well as the corresponding cohorts in the Windows team to see how what it would take to make this into an interactive entity. And of course, the stuff that Kentaro is working on with the Shell team eventually is to take us to having first-class personal video. So thank you all for coming. And this is the team. You saw most of us here, and aided by some wonderful interns that have been with us and coming back again. And if you have any questions, we'll be here to answer them. You can come and see us later, whatever.